Thanks for coming to the channel. Today we'll talk about some driver circuit using what do we got here. Actually, for this video you need to ignore this side of the board, okay? Sorry about that, but I'm working on something over there and I just don't want to take it apart right now, so it's just going to be the middle of this circuit over here. Now, basically what this video is about, the general theme. What is the general theme? The general theme of the video here is how do we, here's a light bulb. It's a 12 volt light bulb. It's 13 volts, whatever. And the question is there's a decent amount of current. I mean, I could already feel the heat. It's just it's a incandescent light bulb. Incandescent light bulb. It could be a motor, right? It could be anything that we're powering. DC, we're talking here. But the question is you have a module, and you'll see this in cars. This is a big time use in cars, and actually a lot of devices, where you have a computer module. Now, what I have in my hand here, this is a Wi-Fi module. This is a ESP01. And it uses this famous chip, the 8266 something or other. Anyway, it's a Wi-Fi module. It's basically a computer. It runs at 3.5 volts. Very low power, very minimal voltage. It might be 5 volts. You may have computer, but you're not going to see computers above 5 volts unless it's some kind of really exotic, vintage, kind of weird thing. So this is 3.3, but it could be 5. Same difference. You're way down there. You're very low. Whereas you have something like this running at 12 volts, and basically you want to control it with a computer, right? I have all this intelligence here, and I want to control this with that. So how do we do that? Like you just sit down and you look at it, you're like, wait a minute, what are you talking about? This is 5 volts. How do I hook up this light bulb to this thing? Because this thing's got to control it, right? So this thing's got to be somehow hooked up to this light bulb. And that's the question of when that comes into play, is the idea of the common emitter circuit, which is, what do these things have in common? And just cutting right to the chase, the thing that they have in common is ground. Okay, this thing is nowhere near going to be anywhere near 13 volts. It can't hold 13 volts up there to run anything. And look at this thing. This has no capacity for current or power. This thing's going to get fried up. You try to move anything through this. So all this thing can really do is say, yes, I want it on, I want it off, and tell us somehow. And it'll tell us by just on one of these pins, it'll give us a 3.3 or a 5 versus 0 volts, right? 0 or 1, right? In digital, we all know that, 0 or 5 volts, or in this case, 3.3. So this video is about this circuit here, which is basically what we have is we have 3 items. Now, what you'll see in most of the time, this will be all packaged up inside of one nice small, I should have had one handy. This will all this circuitry. Sometimes you'll have Darlington resistors. That's very common. Darlington resistors are when you pair up 2 resistors and you're basically multiplying their amplification, their current amplification, which is a whole discussion, because it's not like what you think of amplification, which is typically going to be voltage. Anyway, I digress. So basically what we have here is we want to be able to control a big voltage with a tiny voltage, which seems like at its surface kind of difficult, but we do know the one thing that they both share, and that is a common ground. So if you're familiar, you probably are familiar with breadboards, but just let me review real quick. There are on the outer edges of the board, is where we typically put our power. This board isn't marked. Some boards are marked, so I have the positive on the outside. But what I have here is I have this section up here is actually 13 volts right here, and then the whole rest of the board is 5 volts at the positive. And it's jumped back here, behind here where you can't see it. And remember, ignore this circuit over here, this behind that I'm hiding. And the ground is ground. So the inner rail on both sides is the ground. Okay, and the way that these work is they're connected acrosswise, so they're not connected length. These are connected lengthwise. These four, 1, 2, 3, 4 are connected lengthwise, but all of these are connected horizontally. So, for example, if you look at this MOSFET right here, right, these three pins are isolated from each other, but like this pin, for example, is connected to this wire. So this pin is actually grounded. You can see right away without really too much analysis. This thing is grounded. This is the output pin. This is the source of this MOSFET, which is actually has a flyback, what do you call it, flywheel diode? Whatever. It's not necessary, especially in the case of a purely resistive load. It's just another whole other different discussion. So, but basically what I want to talk about is how this configuration ends up working. Now, I think I mentioned it and I kind of left it, but this is a 56K ohm resistor. And my point in mentioning that is just take my word for it. This is 5 volts up here, right? So if you have 5 volts and you put 5 volts across 56,000, I don't know. Somebody do the calculation. It's going to be less than a milliamp, I think. Right? So what I'm going to do right here is, there's no reason for this loop. There's nothing special about this loop. It just makes the wire shorter. I'm going to connect that. Now, I was actually expecting that light bulb to go on, but how could it go on if it's not connected to anything? So I'm just going to go right to the chase. I'm going to connect up this circuit. Let's see, I always got to use these tools. I can connect up this circuit the way it's supposed to be. So you can see the light bulb is on, and I can actually control the light bulb by simply supplying 5 volts to this resistor. Now, remember, the amount of current going through this wire, based on this 56,000 ohms at 5 volts, it's negligible. It's small. It's tiny current. So clearly, the current coming in through this wire is not powering this. Right? So the current coming through this wire is really just biasing this transistor. And I have a drawing, so I'll get to the drawing in a second. But the current is basically, these transistors are in a simple emitter, grounded emitter configuration. So their output is actually an inverted output at the collector. I will get to that on the drawing. Basically, these are two inverters. Together, they're just they're just sending the signal without inversion to the MOSFET, which is ultimately grounding the light bulb. Now, what's interesting about the common emitter configuration is the fact that it does ground. And you're like, oh, well, that's not special. But what I mean by that is, if there's none of this circuitry and all we have was this light bulb and a battery, and let's just say for the purposes of battery, this is ground and this is 13 volts, so let's just pretend this is a battery. If we have a light bulb and we want to make it run, we'll typically just hook it to the battery. Okay, great. Congratulations, the light bulb is running, right? Thank goodness the light bulb works. Jeez, what's my problem here today? So, typically when you would hook up, if somebody says, why don't you put a switch on it, because I don't need it on all the time and it's going to run out. Yeah, of course it makes sense to put a switch on it. Now I would typically take off the positive and put some kind of switch and a wire, and you would have your switch, right? And on and off and on and off. But the interesting thing about the common emitter is that you leave the power, and you actually, the act of switching is at the ground. And the reason it's at the ground is, remember we mentioned before that the only thing common to these two guys, or whatever they are, is the ground. So what we can do is we can tell, something smart can tell something dumb, hey, just ground this thing. It doesn't have to go up to 13, or could be 30 volts, could be even higher. It doesn't have to go up to those levels and sort of control it directly. It can just sort of sneak through the back door and just say, well, let's just ground it. Because grounding, and a lot of times you'll see this in a car or a vehicle, where you see a device and it's fixed to the positive, and if you're not used to it, you look and you say, wait a minute, this thing is fixed. It goes to a relay, or maybe it goes back to some box, but it's fixed to positive, and then you can measure it. And actually, that's how cars will actually throw a light, is because they'll know. Right, the end of this wire is actually the same voltage as this. If there's no current flowing through here and there's continuity, the end of this wire is going to be this voltage right here. So a computer can look at that voltage and say whether or not a light bulb is shorted out. Or, for example, a more typical example is the heater coil inside of an oxygen sensor. Well, typically, the computer will run a current through, and if it doesn't see at the other end, as long as there's no current flowing. See, as soon as there's current flowing, you won't have 12 volts here, right? Because if I ground it, obviously, if I ground this cannot be 12 volts anymore. And if that doesn't make sense, what happens is all of the voltage is occurring now across where the light bulb is lit, inside of this light bulb. So you will actually now see ground here and 12 volts here, and the voltage and all the power is dissipated, of course, in the light bulb. Okay, that was a little bit of a digression, but the continuity thing is important. So to ground it is just as legit as to sort of connect the power. So I have a video on my other channel about this a little bit more. I don't go into the circuitry, but so let me grab over here. I have a bunch of these, right? These SO ESPO one. So I have one here. Did a little work on it, and right before the video, I broke one of my wires, but it's not the important wire. I need this wire. So basically, you can see back here, I have ground and power hooked up, and let me plug this into that. Okay. Now this board, this is a Wi-Fi board. This is powered on, and what I'm going to do is I want to control this light bulb with. This is going to be a very weak 3.3 volts coming out of here. But remember, this thing is not even going to let hardly any current come through. So this board is naturally isolated by 56,000 K away from this whole circuit over here. So now what I happen to do is, because I am a multifaceted individual, I happen to have a Xamarin app that will talk to this Wi-Fi. At least I expect that it will talk to this Wi-Fi. And turn this light bulb on and off. So let me see if this will work. Turn on. Look at that. I can set the level too. Look at that. I can set it to dim. I mean, I was thinking about making it real time as you slide the slider, but over a network, that's a little bit much, so I'm not doing that. So you have to set it and then hit set. On a WPF app or like a Python app that I wrote on a interface right on top of a GPIO unit, I did do that, and it's very nice when you move the slider and the dimmer just moves with the slider, but not in this case. But what you can see over here, that blue light, this blue light over here, I don't know what to use as a pointer. This blue light over here is doing the opposite of what this is. This is like, not all these modules have this blue light, and the blue light drives me crazy. So the blue light is kind of meaningless. I think it's so that, like, if you buy this thing, which is like $7, I'm serious. This was $7. This board back here was like 2 for $11 or something. I mean, it's ridiculous. Of course, you have to have your programming all ready to go. So obviously, if this thing's getting and actually this will start getting warm after a while. This board is completely isolated from what's going on over here in this driver circuit. All right. So that was great show and tell, right? Okay, so let's talk about the circuit a little bit. Move this off to the side. I think my magic application, that's Xamarin, by the way, using what am I using for that? I'm using Visual Studio 2019 with the Xamarin. Okay, so I'm trying to talk to you guys while I am adjusting my videography thing here so that I can get myself all together. All right, so let's talk about some circuits. Let me get this camera. Is that all right? I got a manual focus. There we go. Let's get this. There we go. That's a little better. All right, we got wires coming all over the place. What's this thing? My windscreen came off, man. All right, so let's go over here. Let's put the windscreen back on. All right, so I guess I could put this circuit in view, right? Okay, we could do that. I don't know. Okay. Anyway, so so here we go. What we have is we have ground across the board for all of these transistors in the MOSFET. They are all, if you look at the board, each one, like remember we were talking about the pins? You don't get the, we don't have a whole lot. Let me fix that light. Let's see if I get that light. Come on. Yeah, that's, well, Okay. So this pin, obviously, should be obvious, is connected to ground. This transistor also, its emitter, these are NPN transistors, by the way, as noted here. And this is a MOSFET, N-channel MOSFET, enhancement mode MOSFET, right here. And also this first transistor, the NPN, also has a pin, if you can see behind here, grounded. Okay. So the circuit that we see here on the diagram is exactly what's on the board here. So I'm not going to go crazy pointing this and that and everything else, but we can basically look at what's going on here. And basically all the way over here outside, which is sort of irrelevant, is this computer, right? Because we're not talking about this computer. All we know is that this computer is going to give us 3 volts, 0 or positive, and that's going to result in this load being activated or not. And now basically, let's take the case where the voltage is high. If the voltage is high here across this 56K transistor, what you're going to get is you're going to get at least a maximum of 100. Well, there's a beta, right? There's a. All right, let's. Geez, I'm not sure what to talk about first. Basically, okay, let's just talk about the circuit. Basically, when this is high, it pulls a current through here. And when there's a current running from the base to the emitter, you're going to get a... Now, this is operating in a switch mode, right? So you're going to be thinking in simple terms, in full on or full on, full off. There's a lot of interesting circuits out there, but a lot of them are talking about amplification of AC signals. A lot of them don't even say that we're talking about AC signals, but that's where you're going to see a lot of capacitors and transistors, and they're trying to bias the voltage sort of in the center right here. Let's say we're using 12 volts for an AC. This is not the case here, but for just to differentiate what we're looking at here, you're going to see other circuits where they're going to try to bias the voltage right in the middle of around 6 volts so that you can swing up and down. This is not that. This circuit is about turning on and off a load, right? So we're using these in saturation or complete cutoff, which is a much cleaner way of dealing and a much more simple rock-headed, like blockhead way of using transistors. The idea of doing amplified amplifiers with frequency response, it has a much richer study, and one I suggest you pursue. Anyway, but this is simple. This should be simple. Because this is using very simple laws. Just interesting how some of these work internally. I don't know how. I'll go into that afterward. But basically, let's take a high signal. So it's high here, which basically is going to turn this transistor on, which means current's going to flow, right? So if we have current flow through this 100K resistor, the 100K is like nothing compared to it. But basically, this is going to be touching ground. So basically, this point, when this is high, this is going to be 0. Right? When this is on, current's going to flow. It's going to pull this down to, as current flows through this is going to drop to 0, or a tendency to go towards 0. Nothing's ever going to be perfect. If this is off, then this transistor is going to be off. This thing will have no connection to ground, and therefore the voltage up here will be high. So when this is off, the voltage here is high. When this is on, the voltage here is low. See, it's an inverter. Okay, the 100K resistor, these resistor values are very just a sloppy. I did not do one calculation, one in my head, about 56K over 3 volts, just to kind of get an idea of what that current was. I didn't even do that calculation. I still don't know what the number is. Anyway, so I just wanted a gigantic resistor here, but not so large I couldn't get any current through. So I said 100K at 12 volts. Right, that's really going to be a small current, but enough to establish, but a current nevertheless. And And as we turn this on and off, that current will shut on and off. And then the 100K over here, it maybe didn't even have to be there. Maybe I could have just connected it directly, but I sort of have this thing about connecting silicon to silicon without anything in between. Darlington resistors aside, transistors aside, I just do that. So 100K, so this is like stage 1. Stage 2 is exactly the same thing, except it would be doing the opposite. So when this is high, this is going to be low. So now when this is high, this is low. But because this is low, this is high, right? So when this is high, this is high. When this is low, this is low. And that's the whole point of this whole stupid thing here. Because there's really nothing going on. We're just taking what the output is. So when this is high, it's high here, and when it's low, it's here. And then here's the same thing with this MOSFET. All we need to do, now there actually isn't any current flow here at all. All we need to do is bring this voltage just a little bit up. It's a specified amount, but of course we want it to saturate, so we don't care. We're going to bring it, as high as possible, which would be 12 volts. But of course it's not a problem because there's no current. There's actually no current going to be flowing through here. So this voltage is, when this goes high, is going to ground this. Okay? So when this is high, this thing becomes like a short circuit. When this is low, this becomes a piece of plastic. And that is how, and that's the beauty of a MOSFET. There's basically, this becomes a very low resistance, especially in these enhancement mode MOSFETs. The load here has this diode on it. I drew it on here because it's on the circuit. And the I don't know where I was talking about that. When you have an inductive load, anything with a coil on it, just like a capacitor tries to sort of smooth out voltage, a coil tries to, it's a completely different phenomena, but it tries to sort of smooth out and maintain current. So the thing is, when you have a load, and you see it when you unplug something, you see a spark. When you have a coil hooked up and you immediately disconnect it, that coil wants that current to continue, but the only way for the current to make that coil, the only way for that coil to make that current continue, which is impossible, is to up the voltage. So you will always see a spike. Whenever you disconnect a coil that has a current currently running through it, not a voltage, but an actual, well, yeah, voltage would actually, well, no, you have to have a current. The coil, if it has a current running through it, when you disconnect it, it will spike. And you put the diode here so that when it's the spike will be in the opposite direction. And the spike will just short itself out rather than going into your circuitry. So that's flywheel diode or something. There's a lot of different terms for that. And there's different configurations. This is the most simple. This is the most simple circuit here. This is the most block-headed simple circuit that you'll see. You'll see some capacitors and things on this circuit board, which are mainly for the voltage regulator, because what you'll find is when you start putting interesting things like computers and things on a regulated, this is a 5-volt regulator, right? This is just like, right, this is just over here on the left side, right here. This is a 5-volt regulator. It's got, it's taking this, basically what I'm doing here is I'm taking 12 volts, bringing it down to 5, and then bringing it down to 3 point, right? So I got like these 3 tiers of voltages. What was my point mentioning the 5 volts? What was the point? Okay, now I forgot what my even point was mentioning that voltage regulator. With capacitors on the board, what you'll find is when you put noisy things like computers and things on the board, that the voltage regulators absolutely need the right capacitance there in order to regulate the voltage. That's what I was trying to say. This seems to be working just fine without any sort of coupling capacitors or anything like that. And I just wanted to go a little bit into an interesting thing about how the NPN versus the MOSFET technology works. The MOSFET technology is to typically say this is voltage controlled, and then they'll typically say that the NPN or the traditional transistors are current controlled. It's like, well, what the hell are you talking about? There's voltage and current going on in both of these things. And it's like, yeah, man, it's like people like to get everything all kind of, but it is true. For example, the whether or not current will flow through here is based on what the voltage is here. Now you could say the same thing here, but really the amount of current that can flow through a transistor here is really linked to the amount of current flowing through here. If you look at this picture here, this is basically an NPN transistor, where you have the input basically has a built-in diode, but the diode is in the direction of the flow. So it's not like this diode up here, which is like in the opposite direction, and it's just sort of like under normal conditions is just a an open circuit. Here you're going to get your 0.7 volts or whatever. So yes, at every NPN transistor you have to overcome 0.7 volts here before this thing starts turning on, because there's a built-in diode right there. But the thing that's interesting about a NPN transistor is it's like a gear. The amount of current flowing from the base to the emitter is related by a factor of something, usually 100. They call it beta. And it's like having a gear. It's like a 10-speed bicycle, right, that's geared. For every one spin, this will spin like 10 times, right, or 100 times or something. So what it's saying is that whatever current comes through the base, the maximum that will come through here is 100 times that base. So you can actually create a current limiting situation using a simple NPN diode by simply limiting the current. And you limit the current by the resistor. Because, right, by superposition, if you're just looking at this diagram over here, by superposition, you can ignore the load, right? That's why I drew this diagram. Because you can analyze one side of the circuit, which is this base to emitter, as its own circuit, right? Just like a diode, right? If LED, right, with at 5 volts, a 330 resistor with an LED diode gives you like a typical bright LED. Maybe 220 volt, like a couple hundred ohms. And you can analyze this way. So you can say, oh, I want 10 microamps to go through here. Well, then that means only whatever 10 times, whatever the beta, right? It's a specification of the device, right? You'd have to look. I always just assume 100. It can be less and it can be more. The more powerful, typically, the less this is going to be, right? On these small, I think these are 3905 type transistors, the beta is going to be 100. So if I just configure this resistor to have like 10 milliamps going through here, and what does that translate into? Like 1 amp? 10 times 100? All right, my math in my mind is all off, so if I'm wrong, but you get the point. A maximum of 100 amps could come through here. It doesn't have to be fixed like this gear would suggest. You could have, if this load uses less than 100 times the base to emitter current, then it'll just use whatever current it needs. But if it's a real shorts, if it's a light bulb or something that's really low resistance, then you're going to hit your maximum current based on whatever your base is. Now you could increase your load current by simply increasing your base. But the beautiful thing is your currents and your voltages here at your base are really low currents and even voltages. Because what the strategy, for example, here at this first transistor is, as it goes on, you're just looking to bring a voltage across this. The whole purpose of this whole setup is to bring a voltage across this or not. You either want this at 0 or 12 volts. And then that will put it across, right? Remember, these are doing the same thing, and you're just, right? So you could ignore one or the other and just look at one and just see what the output is. But basically the point is, when this is at a high, basically this is going to be 12 volts. Well, it's not going to be exactly 12 volts, but it's going to be a very high voltage, which will be plenty enough to saturate and turn this thing completely on. But, and here's the thing, is this doesn't have to be 12 volts. It could be 12, it could be 9, it could be 24, it could be 30. The voltage up here doesn't matter, see, to the computer down here, because it's completely isolated. All the computer sees is this circuit here. That's the interesting thing about this whole driver circuit. It's completely isolated. That's why they talk about high impedance input versus low. Like the impedance here is like almost like is less than an ohm, I believe. It's like point something ohms. Very low impedance, right? Very low output impedance. The input impedance is what, 56K plus whatever that diode. So I just assume it's a minimum of 56K, the impedance here coming in. I say impedance, but we know it's DC, but we'll say resistance. So it's a high, so it's a beautiful thing. This thing is like seeing a nice high resistance, and then it's controlling this light bulb with a really low resistance. And one of the interesting things is you could do a lot of stuff with these transistors. Another thing you can, I think I mentioned it, it's a constant current. For example, if you think about it, if you're trying to charge a battery, you can limit how much current you're putting into the battery by just configuring this. Remember, this base to emitter, and this stuff down here is just pertaining to these two. This is really simple. You just bring the voltage high, and boom, this will flow. And there's no current flow between this or this. You're just looking for strategies over here to bring the voltage high, right? And that's all this is. You bring 3.3 volts when it's high. So when this is 3.3 volts, this is going to be 12 volts, right? And when it's 0, it's 0. And that's the common emitter, right? See how everything's common to the emitter? The emitter is common. Although this is not an emitter, it's a drain, it's still where the current's coming out. So the current is going into all of these. And essentially this is just a switch, right? This is just where we connect. We could just disconnect this and just connect the load to ground if we wanted to, right? And that's a lot of times if we're testing, that's what we will do. If we're wondering if this is any good, we will connect to ground and see if that load works. Or maybe the computer's bad. So we disconnect the computer and connect up to the beginning of the driver and see if the driver works. That's something you almost never see people try. It could be impossible. This may be a connector right here, or this may just be on the circuit board. Your computer connector may actually only be, your connector may just be this right here. So all this stuff may be actually on the circuit board, which is tough. But if you can get in there and you can look, and I've seen Diagnose Dan do this. It's beautiful. Goes on the board, finds the computer. You can see the voltage going up and down here. And right here, because it's an impedance, it's separate. But then over here, something isn't working. This load is not working. I think it was a injector circuit. And these are noisy, nasty circuits on a car. That's why these flyback diodes are freaking critical. Okay, so basically that's basically my little talk on driver circuit. I don't know if that helped or not, but it's a pretty cool thing. I got this. All right, I'm gonna put this. All right, yeah, you could reverse the video if you want to see. I think that was on there pretty good, right? I'm just over here knocking things over, but I just I just love this idea. I think I said it in one of my other videos where I'm a developer. I do all kinds of different things, but I like it where you have this magic stuff happening, and you can see, right? The only thing coming in here is my power supply wires. So I got whatever, 13 down to 5 down to this is just errant wire. That was the one that was broke. But you can set the level. I love this thing. So but and actually let me see. Just real quick, right? Just for the hell of it. Oh, I hate look at that wire. I'm never gonna see, that's never going back in. It's never going back in this video. So let me see. Probably doesn't matter. Yeah, let's try. This should be able to go in reverse. This is a DC motor, right? Oops, plugged into the wrong one. So I'm plugging into the source. Yes, to the source. Now what's interesting is, no, let me be consistent so that it makes sense on the video. So what I'm going to do is I'm plugging into the power. So obviously if I'm plugged into the power, I'm not powered. Even though I'm plugged into the power, but that voltage right here coming out of here is actually, I know I should measure it, but I'm not going to. It's 12 volts coming out of here. Unless this motor was bad and the coils were broken or the brushes were bad. So let me come over here. Now if I'm just going to touch, you can hear that, right? You can see that, I think. Okay. So, oh yeah, but the video does weird things when things spin. That's kind of okay, I think that's connected. Okay, so let me see. Oh, yeah. Right. So now this is the case, right, where that diode is actually protecting my circuit. Because when I turn that on and I turn it off, there's a little bit of a transient spike going on in there. And then this is the pulse width modulation. I think I did a video on the pulse width. Did I do a video on pulse width modulation? I have to check. Anyway, that's what this is. And I thought about, excuse me, excuse me. I thought about doing this. This app right here is hacked. I stole this from my other app. That's why nothing makes sense here. This is from my OB. Look at this. No, don't even try to make sense of what you're looking at with the app beyond the buttons, right? The only thing that you're allowed to look at are the buttons. But that's the thing, you know. You have brains, and you have brawn, and you have their load, and you have your thinking, right? So it's a beautiful system where you have your thinking part, and then you have your other part that acts in the world, that turns on and off the lights, the radars, the tires, the whatever. That's what makes all this interesting. Anyway, thanks for coming by. I really appreciate it. I hope you enjoyed this. I don't know. I'm just making videos of the technology and things I'm running into. When I see something interesting, I just try to make a video. And I mean, this channel's just there for just thoughts, right? So anyway, thank you very much for coming by. If you stayed this long, really, thank you very much. And to my subscribers, thank you. And have a great day. All right, let me see. I got to figure out how do I stop this thing.